Alrighty, so this video we're going to continue talking about calorimetry. Last time we introduced the main equation that we'll use, which is the heat change by each piece of a system. So that is, if one object loses some heat, another gains heat, and there's multiple objects, you take how much heat is lost or gained by each object, add them all together, and set it equal to 0. That's basically conservation of energy. The total energy of your system will not change if it's a closed system, which for the problems we're going to do, we will assume it's a closed system. Then we saw that for normal circumstances, when an object gains or loses heat, it changes its temperature. Or vice versa. When an object changes temperature, it's because it either gained heat or lost heat. And so the equation for that was Q, the heat lost or gained by an object, is Cm delta T, where C is specific heat. That is how much heat is gained per change of temperature. And that tells you about what type of material we're talking about. M is the mass, how much of the material is changing temperature. And of course, delta T is the change in temperature. And so, all the examples we've done thus far have been exactly this. You have multiple pieces of your system, each one changes temperature in some way, and so we keep track of how much heat is gained or lost, set it equal to 0, and we solve for whatever the unknown is. However, this is only half the story, because we know of examples where an object can gain heat or lose heat without changing temperature. And that is phase changes. Phase change is like melting or boiling, freezing, condensing. So you have water, you freeze the water, it goes from the liquid phase to the solid phase. Or you boil water, it goes from a liquid phase to a gas phase. If you cool down steam, it goes from steam, the gas phase, down into a liquid phase, water, and so on. What we found is that the process of doing this phase change requires energy. So if you want to melt some ice, for instance, you have water that's frozen, so it's solid ice, and you get it down to its melting point. So whatever the melting point is, in case of water, let's say 0 degrees Celsius, well, it's just going to sit there and be ice at 0 degrees Celsius forever. However, if you keep adding heat, it doesn't warm up. Instead, what happens is, as you add more and more heat, more and more of that ice will melt and turn to liquid water. That liquid water is still at 0 degrees. So that means when we have a more complicated system, which involves phase changes, we must keep track of how much heat we're putting into the object or taking out of the object while it's changing phase, even though it's not changing temperature. If all we used was Q equals Cm delta T, the only energy we'd ever keep track of is the energy that makes the temperature change. But then we'd lose all the information about how much energy we had to put into the ice to melt it. It's as if it didn't happen, but we know it does happen. And that's what latent heat helps us with. There's a new Q we now have to worry about, and that is Q equals M times L. In this case, M, of course, is still the mass, but now L is what's called latent heat. And basically what this is the amount of energy lost or gained due to a phase change. And that's per kilogram, of course. So now, every time we do a calorimetry problem, if there's something in the problem which is going to change phase at some point, if you put ice in the system and the ice is going to melt, or if you put water in the system and you know the water is going to get to 120 degrees, you know it must boil first because water can only get up to 100. So you must boil the water. Now it's steam, and that steam can go from 100 to 120. When we have these types of problems to worry about, we now must use not just Cm delta T, we still have to use that, but now we also have to incorporate M times L as well. So, but it's not a big deal. It's just adding one more term, or maybe two more terms, whatever, to each problem we do, if it's required. Let's take an example. You have 800 grams of coffee at 95 degrees Celsius. You then add, let's say, 50 grams of ice, which is currently at -5 degrees Celsius, to cool it down. Find the final temperature. Of the system. Okay, so very similar to the type of calorimetry problems we've had before, only now I have ice in this problem. And this ice can melt. And in fact, I'm assuming it's going to melt. If I put a little bit of ice in a big hot cup of coffee, I assume the ice will melt and cool down the coffee. Because there's melting involved, I know I have to keep track of not just Cm delta T, but latent heat as well. Well, first thing, let me go ahead and give you some information. Let's assume the specific heat of coffee is 4186, just like water. Let's just pretend. And let's assume the specific heat of water, or you know what? This will be better. Let the specific heat of coffee be 4,000. Specific heat of water is 4186, and the specific heat of ice, let it be 2000. Now 2000, I don't think that's really the specific heat of ice. I'm just too lazy to look it up in Google. It's something around 2000, but let's just use 2000 as the number for this problem. Okay, so given that information, I want to solve this problem. The very first step of every calorimetry problem is we need to figure out what is every single piece of our system. That's important. Well, we know coffee. What's going to happen with the coffee? The coffee is going to cool down, so there must be some Q for the coffee. Okay, what else do we have? I don't say anything about the cup that the coffee is in, so let's just assume it's styrofoam. It won't change temperature. So we won't worry about any cup or anything like that for this problem because I don't give you information about it. I do have ice. What can happen with the ice? Well, I already said the ice is going to melt. But in order for the ice to melt, we already know the melting point of ice is 0 degrees. That's the same as the freezing point of water. 0 degrees is when ice melts to water or water freezes to ice. So the first thing that can happen is the ice has to go from -5 up to 0. So I'm going to say Q ice is that piece of the problem. The ice heating up to get to 0 degrees so it can melt. Then the ice can now melt. So I'm going to have another Q which is called melting. Q melt is just the amount of heat required to change the phase. That's the melting piece, the latent heat. All right, now what is it? The ice has gone to zero. It's melted. So now this melted ice is now water. That's what melted ice is. It's water. This water is starting at 0 degrees. And it's going to heat up to whatever the final temperature of this system is. So there must be another Q, which I'll call the Q melted. That is, how much heat does the melted ice take in to heat up to its final temperature? That's all the Q's in my system this time. I set this equal to 0. So notice, when I did a problem like this before, but what I did was I added some cold milk. There was a Q for the coffee and a Q for the milk, and that's it. Because nothing in that system was going to freeze or melt or anything like that. Here, the coffee will cool down. That's fine. That's the same Q. But now there's ice. The ice is going to go through a bunch of different things. It's first going to heat up to get to 0. Once it's at 0, it's going to melt. And once it's melted, it's now going to heat up to the final temperature of the system. So the ice gives rise to 3 different Qs. But there they are. I've done the hard part already. The hardest part of this problem is setting out what are all the Qs that we need for the system. How do you do it? You use your intuition, use your logic, think about the system. Be very careful and think about it one step at a time. What's everything that can happen to the coffee? Well, it's not going to boil because, of course, I'm cooling it down with ice. It's not going to freeze. Ice can't freeze something. So it's just going to cool down. Cm delta T, I just need that Q. Then we think about the ice. Well, the ice is at -5. The only thing the ice can do is heat up until it reaches its melting point. So that's the first Q. Q ice is heating the ice up to get to the melting point. If the ice started at 0 instead of -5, then we wouldn't have this term because it's already at the melting point. We don't have to heat it up first. But in this example, we have to heat it up first to get to 0. It's now at 0. Then what can happen? The ice can melt. It's going to continue to soak up energy from the hot coffee, melting the ice, but leaving the temperature the same. That's Q melt. This is latent heat term. Once all the ice is melted, now what can happen is this now melted ice can continue to grab energy out of the coffee to heat it up until everything reaches an equilibrium temperature. And that's what the Q melted is. That's another Cm delta T because it has to do with changing temperature. All right, now that that's done, let's start putting numbers in. Q coffee, I've got C for coffee, or I'll do it like this, Cm delta T for coffee. Then I'm going to have a Cm delta T for ice. Then I'm going to have an M times L to melt the ice. And now that the ice is melted, I'm going to have a Cm delta T. But this is water. Because once the ice is melted, it's not ice anymore, it's now water. Set this equal to 0. And now, all I do is take all the numbers out of my problem, stick them into this equation. C for the coffee, 4,000. M for the coffee, 800 grams, that's 0.8 kilograms. Delta T for the coffee. I don't know its final temperature, that's what I want to find, final temperature. So I call it TF. Minus the initial temperature of the coffee, which was said to be 95 degrees. Then, I now do the ice. The ice, C for ice, is 2,000. M for ice, 50 grams, so that's 0.05 kilograms. Final minus initial. What's the final temperature the ice will reach? It's not T final. It's not the final temperature of the system. Remember, ice can only get up to 0. So the ice's final temperature will be 0 degrees. That's as hot as it can get. Its initial temperature, -5. Then we have an M times L. The M is still the ice, so 0.05. Oh, that's one more thing I need to give you. I forgot. Let the latent heat of fusion for ice be 334,000. Okay, that's pretty close to the right number. So this is kind of a big number. Let me put it down here. Plus, so ML term, M for ice, 0.05. L for ice, 334,000. Okay, that's just something given in the problem. Last term, Cm delta T for the now melted ice. The now melted ice is now water, so C for water is 4186. The mass, well, the mass of the water is the same as the mass of the ice because that's what it was. It was ice. It's now water. So it's the same mass, 0.05. TF. TF, the final temperature of the water, is whatever the final temperature of the coffee will be. Because once the ice is melted, this water will heat up as much as the coffee will cool down. So TF, which is what I'm looking for, minus what's the initial temperature of the melted ice? It's not -5. That's the initial temperature of the ice. But after the ice is melted, remember, the ice got to 0 degrees, then melted. So the initial temperature of the melted ice is 0. And we set this equal to 0, and we got our equation. So, again, Cm delta T for coffee. I know C for coffee, the mass of the coffee. Final temperature I'm looking for, initial temperature given as 95. Cm delta T for ice. C for ice, 2,000. M for ice, 50 grams. TF minus TI for ice. Well, I know the initial temperature is -5, but the final temperature, I have to remember, this is the term that gets the ice down to its melting point. So that's 0 degrees. Next term, Q melt, that's the latent heat piece. That's M times L. And the last term, Q melted. This is, the ice is now melted. It turned to water, so C for water. How much of it do we have? The same amount as ice. And what's final minus initial? Final is the final temperature of the system, the thing I'm looking for. The initial was the ice has melted, so it must be at 0 degrees to start with. All right, so now we start plugging our numbers in. So we got 4,000 times 0.8 times TF is 3,200 TF minus 4,000 times 0.8 times 95 is 304,000. Next, 2,000 times 0.05 times 0, that's 0. Minus, or minus is now plus, 2,000 times 0.05 times 5 is 500. Plus 0.05 times 334,000, that's 16700. Plus 4186 times 0.05 times TF is 209.3 TF minus 4186 times 0.05 times 0 is 0. And we set all of that equal to 0. Now we see we just have a big long equation with a whole bunch of numbers and terms with TF. So we want to keep TF on one side, put all the numbers on the other side. So 3,200 plus 209.3 is 3409.3 TF. On the other side, we have 304,000 minus 500 minus 16700 is 286,800. We want to get TF by itself, so we divide both sides by the 3409.3, and we get that TF must be 84.6 5.12 degrees Celsius. Before I box it, I find out, does this make sense? Well, my hot coffee started at 95, and my ice is at -5, so I know the temperature has to be between -5 and 95. I get 84. The coffee cooled down. That seems okay. So there we go. Final temperature of the system, I put enough ice in there to get my coffee down to 84 degrees. And that's how we handle these new problems. Notice it's identical to calorimetry before. The only difference is now that we allow things to melt or to boil, we have extra terms which allow for the melting or boiling. And that's your latent heat term. So it is a little more complicated. You do have to put a little more thought into thinking about each piece of your system. But once you've done this piece right here in yellow, once you've laid out what are all your Q's, the rest is pretty much, crank the machine. Each Q is a CM delta T or an M times L. Anything where the temperature is changing, those are CM delta T pieces. Anything where you have a phase change, like melting or boiling, that's M times L pieces. You lay them all out, add them all up, set them equal to 0, and then you just plug all your numbers in. Where can things go wrong? First place they can go wrong is not doing the yellow piece correctly. You forget that you had to heat up the ice first. Or you forget that once you've melted, there's still another term to worry about, which is now that the ice is melted, it can continue to heat up. Another place things can go wrong is when you're plugging numbers in, right here for the ice, final temperature of the ice is not the final temperature of the whole system. The ice is not going to get that hot. The ice can only go to 0. So the final temperature of the ice will be 0 degrees. Likewise, the last piece over here, after the ice has melted and turned to water, what's its initial temperature? Its initial temperature is not the same as the initial temperature of the ice, because it's not ice. This is a different thing. The ice has already warmed up to 0 and then melted. So the melted ice is starting at 0, so his initial temperature must be 0. If you could remember those things and not make mistakes there, the rest is free and clear. Plug the numbers in, multiply everything out one at a time, collect all the TFs on one side, everything else on the other. So, this will finish up calorimetry for us. You now know all there is we're going to worry about for calorimetry. Any problem I give you will either just be, as last week, CM delta T stuff, or as this week, a combination where there can be phase changes as well. Either way, you're starting with this yellow circle where you have all the Q's lined up. Once you have all the Q's, you then plug in all the numbers and you get your answer. Just be very careful to understand what are all the pieces that are important to you. If in this problem, I put the hot coffee in a metal cup, an aluminum cup, let's say, there's going to be another Q sitting there for the aluminum cup, because obviously the cup will be hot with the coffee. When you put the ice in, not only can ice take energy away from the hot coffee, it can take energy away from the hot cup too to cool it off. So there'd be one more Q in my yellow circle here. That would be Q for the cup. Another CM delta T. So you just read the story, logically think about all the important pieces, set a Q for each piece, and then go from there. So I hope this makes sense. I will be, of course, the practice problems are already posted, so I'm sure you've already seen on that set some problems that deal with latent heat. Now you know how to work with them, so you can continue working some more practice problems, those that have latent heat in them. And those will be a lot more easy to understand now that you know what latent heat is. I will be doing another video giving some example problems from this. And of course, look out for a future homework problem with latent heat involved sometime this week. But other than that, that's all I have for you this week. We'll talk next time.